Okay. Assalamualaikum and a very good afternoon. Again, I am Dr. Faizwan Abdullah, your lecturer for the and the coordinator for the SSCK1891 Analytical Chemistry Practical. Right. We now today we'll do the virtual lab for the experiment 3, which is about determination of what? What we'll do today, definition of zinc by linear calibration and standard addition methods using atomic absorption spectroscopy. So the focus is now on the atomic absorption spectroscopy, right? The instrument, how the instrument works, right? So I will show you a very short video first on how the AAS works, only for for your just an idea how the instrument is, right? Okay, wait for a while. Right, guys, can you wait for a while? Can you hear the video? Can you hear the video sound? Oh, tak dengar. Wait, I think some setting. I'll wait for a while. Farhan Haji share dengan sound sekejap saya tengok macam mana. Saya dah dia dah setting dah sebenarnya. Oh, okey. All right. Okay. Now you can hear, I think.
This animation of a flame
Can hear?
spectrophotometer will provide an idea of how the machine works. The
Alright.
analyte is taken into the nebulizer where it is vaporized and conditioned to provide the best sample for the flame. The radiation source sends light through the flame and into the monochromator. In the monochromator, the beam encounters a series of mirrors that separate the beam from any background light and noise that is not necessary for analysis. This filtered beam finally hits the detector, which relays the data to the analysis software. This is the gas that feeds the flame. These are the lamps that provide the source of radiation. The lamp is specific to the analyte. The analyte is taken into the flame by this capillary tube. Data collection is performed by software installed on a computer. This demonstration will use a sample of copper. First, start by cleaning the sample capillary with a chem wipe. Then, insert it back into the sample to be aerosolized, mixed with gases, and released into the flame. The flame turns a green color that is distinctive of copper. Waste is then siphoned off into a collection bucket. The data is then sent to the computer for analysis.
Okay. That's all. Only a brief introduction on the AAS. Oh, sorry. Okay. All right. That is a brief introduction on the AAS. What is AAS? Atomic Absorption Spectroscopy. Yes, good. Okay. All right. So we have this instrument. Okay. For the first experiment, if you can remember, okay, for those who have done in the physical lab for experiment 1, right, and also for a majority of us have listened to me and other lecturers in the virtual lab session last 2 days for the experiment 1. It is the classical method. We call that as a classical method to determine, to measure or to determine the metals in a sample using a gravimetric analysis. What is gravimetric? It is gravity, okay, based on gravity word, meaning we measure the mass, right? Okay, we calculate or we record all the weight of the precipitates, okay, with the crucible before and after, all right, and then we calculate how much is the precipitates, and then after that we can determine how much is the metals, okay, that already react with our precipitant, right? That is a classical method. It's quite messy, right, to handle, and then use a lot of time, consume a lot of time, and a lot of error also can might be occur along the the analysis process, right? Because it involves some reactions, all right, and maybe some of the our analytes which is our metal for previous experiments, nickel, right, might be left on the sample containers, all right, and so on. But we have a modern instrument called as atomic absorption spectroscopy, okay, or the instrument called as atomic absorption spectrophotometer, all right. So the concept is, all right, it's quite easy. Okay, let me share again just the just the static figure of the AS concept, right? Okay, so the concept is we have three important things in AAS. Okay, the first one, the name of the instrument is atomic, right? Atomic. So what's mean by atomic? We have flame atomizer, if you can see here, right? If I can annotate here, right? We have a flame atomizer. Okay, what is the function of the flame atomizer? Of course, it has a flame here, right? It has a flame here, right? From our, we have a source of flammable gas that we use, air combination, air combined with acetylene, and also we have nitrous oxide and so on, depend on the analyte type of metal that we're going to analyze, right? And then we create a flame here at the flame atomizer, so that the sample will be pumped in the flame atomizer, and when come to this stage, the solution sample, of course, when using AS, we are dealing with only the solution sample. If we have a solid sample, we need to transform into solution. How? We call it as digestion, right? Right? We digest the solid sample into a solution sample, right? We must make sure that it will become the liquid sample to analyze with AAS, right? Then the flame atomizer will atomize it. It will burn our sample, right? It will burn our sample in the flame atomizer and ensure that our the metals, the analyte of concern in the for example, we want to analyze today, okay, zinc element, right? So to make sure the zinc is well atomized in the flame, and we have I told you we have three important parts. The first one is flame atomizer, right? And we have the second one is the source of light, okay, to give the light with the same wavelength of the analyte. For example, today we want to detect zinc, so the hollow cathode lamp, remember the name hollow cathode lamp, right, will produce a light with the same wavelength with zinc, all right? So that is the second important thing in this instrument. And the third thing that's really important is our detector. All right, how it detects the hollow cathode lamp will emit, okay, we produce a light with a specific wavelength depending on our analyte, right? Remember, AAS only can detect one instrument in a time, one element in a time. Sorry, not instrument. This is instrument. One element at each time. For example, zinc. We need to put hollow cathode lamp with the zinc light, right? To detect another metal, copper. So we need to put a hollow cathode lamp with the copper light. So today we use zinc, all right? And then what happened is the third part, the detector, right, will detect the if we have zinc in the sample, the detector will detect a loss of energy from the light source, from the hollow cathode lamp. So how much is the energy loss, right, represent how much is the zinc, right, zinc atom inside the flame that have been atomized by the flame atomizer, all right, absorb, right, the sum of the energy in the produced from the hollow cathode lamp. So that the amount of energy loss represent how much is the zinc, okay, in the sample. So let's say if we don't have zinc in the sample, what happened to the energy loss detected by the detector? Someone can give me an idea? If we don't have zinc, okay, in the sample, do the detector detect the loss of energy? Yes, someone? Right? Okay. No, right? Because there is no, right? There is no zinc in the sample, right? if there are zinc, then the detector will detect the loss of energy from the hollow cathode lamp because it absorbed by the zinc in the sample that have been atomized. All right, that is I only remind you on the topic that you have learned, I think, in the analytical chemistry for those who took the course, right, on the AAS concept. All right, that is the basic concept of AAS. We have 3 important parts in the AAS. All right. Okay, I will stop sharing. Meaning that you understand well about the basic concept of the AAS instrument. All right. Then I think I should start to share the experiment 3 video. Okay, you ready, guys?
Yes, doctor.
Okay. All right, now let us watch about the experiment 3. Okay, determination of zinc by linear calibration and a standard addition methods using atomic absorption spectroscopy. All right, so our analyte today is zinc. Right, we will detect the zinc in the sample using using AAS instrument with 2 different techniques. The first one is the linear calibration, right? Meaning that we prepare a series of the calibration solution, all right? And then the second one through the standard addition methods, all right? Meaning that we prepare the series of the calibration solutions for the instrument, but with together with the sample inside it. Okay, that is standard addition method, right? So I think most of you have no idea what is this. Okay, let us watch the video first, right? Sound? Right, what happened now? Guys, can you hear me?
Yes, doctor.
Okay, sorry, because I think there's some problem just now. Some of you have do the annotation request. I don't know. Okay.
Hi, I'm Dr. Faizwan again. Now, I'm going to explain to you about our experiment number 3, which is determination of zinc by linear calibration and standard addition methods using atomic absorption spectroscopy. The machine decides me. Atomic absorption spectroscopy is a technique for determining the concentration of metal element or mineral in a sample. The technique can be used to analyze the concentration of over 70 different metals in a solution. It uses absorption or emission spectrometry to assess the concentration of analytes in samples. Electrons of atoms in the atomizer are promoted to higher orbital for a short amount of time by absorbing a quantity of energy of at a given wavelength. In a particular element. This gives the technique its elemental selectivity. Quantitative analysis requires accurate and reliable measurements that relate to the composition of the sample. In instrumental techniques, the proportionalities need to be practically established in the calibration procedures. In a typical simple calibration, a range of standards is prepared containing varying amount of the analyte. So now we are going to use this technique to determine zinc in our sample using AAS. The first step of this experiment is the preparation of the stock solution. We require 1000 ppm of zinc. This can be done by measuring 0.44 grams of zinc sulfate to the nearest 0.1 milligram with 4 decimal places. This is what I'm doing now. I'm transferring the standard into the beaker and weigh. Now I get the amount that I require, 0.44 grams. The next step in this process is to prepare the solution. I am going to dissolve the 0.44 grams zinc sulfate in 100 milliliter of deionized water for dissolving the salt in the ionized water. Stir it, right, to make sure that it is homogeneous, right? And then the next step, of course, after preparing this, I have to transfer into 100 milliliter volumetric flask. Right. So now let us prepare this first. Okay, we stir. Right. Then get our volumetric flask. Then we can start transferring the solution into 100 milliliter volumetric flask. This is how it is going to be done. Then we add distilled water, the ionized distilled water, into the volumetric flask up to the mark. We have to be very careful. We have to make sure that we have eye level observation. Now, okay, since it's coming to the mark, I have to stop it. I have to make sure that I am at the level. Right. Now I'm transferring small amount using dropper, small amount of the ionized water using the dropper to make sure that the meniscus attains the mark that I want. Now it's about it. I think we got it. Yeah, just a little bit, one more drop to go. Yeah, that's it. Fantastic. Now put up the cap and make sure that you mix the solution by flipping this up and down for several times to make sure the homogeneity of the solution is prepared. Now you have the 1000 stock solution. Since we have done preparing the stock solution of 1000 ppm zinc, the next step is to prepare the working solution. We need to prepare 10 ppm of working solution from the stock solution that we have prepared earlier. Now I'm going to show you how that can be done. So I am going to pipette a certain amount from this standard stock solution that I prepared earlier. Right? I'm going to pipette that out. Okay, and I would like to transfer that amount of stock solution that I have prepared. Okay, let us get the volume into the next volumetric flask. Right? Well, you have to calculate that. I'm not going to tell you the amount. M1V1, M2V2, guys. Right, so since I have already transferred certain amount of the stock solution into the next volumetric flask, now I'm going to fill up the volumetric flask with distilled water right up to the mark, the same process that I demonstrated earlier. Right, so upon attaining to the mark, I should be able to get my 10 ppm working solution of zinc. All right, just pipette a little bit more to make sure that we get to the mark. Okay, a little bit more, maybe a little bit more. Right, I think a few more drops maybe. Okay. Okay, a little bit more. A little bit more. Carefully, be sure that you get the meniscus right to the mark. Okay, I think I got it. Now, I have to cap this volumetric flask, and the same process I have to flip upside down several times to make sure that the solution is homogeneous. Now I have the working solution of 10 ppm. Next, I'm going to prepare the calibration standards, right? So I'm going to need 5 different volumetric flasks because I have to prepare 5 different concentrations of calibrators at 0.5 ppm, 0.4 ppm, 0.3, 0.2, and 0.1 ppm. Right, so to prepare this, I have to prepare using serial dilution. I'm going to take certain amount from the stock solution and transfer into the first volumetric flask to prepare the 0.5 ppm, and then transfer certain amount from the first volumetric flask to the second volumetric flask to prepare 0.4 ppm, and then to the next, right? So using the serial dilution process. At the end of the day, I'm going to have 0.5 until 0.1 ppm. So these are the calibrators that I'm going to use to prepare my calibration curve for determination of the zinc. The next step is I'm going to prepare the standards ensemble for standard addition method. I'm going to transfer 20 milliliter from this sample into every single volumetric flask here. And then I'm...
All right. I would like to ask from all of you. Okay. You can see that I'm preparing the a series of calibration solution, right? A series of calibration solution from 0.1 to 0.5 ppm. Okay. What is ppm? Anyone? What is ppm? What is ppm? Part per million. All right. Meaning that a milligram per liter, right? And so on with the similar amount. All right. Okay. As I told you about the theory and the principle of the atomic absorption spectroscopy, okay? All right. The instrument will detect the absorbance, right, from the analyte inside the sample and detect what is the energy loss in the detector. So that is the concentration of the analyte inside the sample. Now, I would like to ask you a question, right? I would like to stop sharing first. Okay. Wait for a while. All right. In the chat room, please open the Mentimeter. I put a link there. Okay, I will share the live of the Mentimeter. Okay. My question is, could the AAS instrument directly detect the concentration of the metals in our sample? Meaning that we put the sample to be pumped into the atomizer, the flame atomizer, And then with the detection of the energy absorbance, right, loss, the energy detector detect the energy loss from the energy source, which is hollow cathode lamp, and the detector detects some energy loss due to the absorbance of the analyte. For example, today we have zinc in the sample, and the AS will directly tell us this is the concentration. Can the AS do that? Okay, yes, no, or don't know, please vote for that. I actually want all of you vote for this, right? Right? Answer it sincerely if yes, no, or I don't know, okay? Because you don't have your identity shown here, okay? It's okay. Right? Please vote for it. Could the AAS instrument directly detect the concentration, right, of the metals in our sample? Okay. Yes, no, or I don't know. Okay. Keep on voting, guys. Keep on voting. Okay. Done voting? Oh, we have some more. Okay. Right, done voting? Okay. All right. We have done voting. Okay. So almost how many there are more than 80% have answered no. 16, sorry. Okay, sorry, I have some internet difficulties now. Guys, can you still hear me? I don't know what happened now. Okay. Hey guys, sorry.
Wait for a while.
All right, sorry guys, we have some problem just now. Okay, 83% say no. Right, and then about 16% said yes. The AS could detect the concentration of the metal in the sample, and 10% said that I don't know. Right. So, it's not a wrong thing for you. You don't know or you answer a wrong question because we are in the learning process. Okay. Every time I taught my student, okay, I always say that in the analytical chemistry, okay, I also said that all the analytical instruments are, if some of you have learned the about the experiment 3 from me, I think I told you that all the analytical instruments are, the word is quite harsh, okay, instruments are not clever. Or in other words, the instruments are quote unquote stupid. All right, not clever. Because, for example, AAS, atomic absorption spectroscopy. Okay, we'll watch again the video after this. Okay, atomic absorption spectroscopy. It only can detect the absorbance, right? For example, I've told you, if the detector detects the loss of energy from the energy source, which is hollow cathode lamp, right? Because due to the absorbance of the energy from the light source, the absorbance is due to the absorption of the energy from the analyte. For example, zinc inside the sample that have been atomized. The instrument only give the information, okay, in the display system to us. All right. This is the absorbance of the energy. The instrument cannot tell us the concentration of the analyte. All right. So what we need to do, that's why we have this experiment 3 for us to teach you on how to teach the instrument, right, to tell us precisely, okay, right, accurately the concentration of the analyte through the preparation of the calibration solution and also the standard addition method. Okay, that's what we are doing previously. We have shown you a video, right? The virtual lab video. I was preparing the series of a calibration solution, a known concentration. We know the concentration, right? In the video, we have told you we prepare 0. How much? 0 0.1, 0 0.2, right? Am I correct? The concentration that we have told you in the video, 0 0.3, 0 0.4, 0 0.5 ppm. But at the first place, what did I do in the first place in the video? Prepare the stock solution, right? How much is the concentration? Anybody can tell me how much is the concentration of the stock solution that I have prepared previously in the video? How much is the concentration? 1000 ppm, right? From 1000 ppm to 0.1 ppm. Can I dilute it directly from 1000 to 0.1? You know the equation, right? N1 V1 M2 V2, right? What is M1 V1 and M2 V2? Can anybody open the mic and tell me what is the equation? Anybody? Anybody can tell me the equation? What is the equation M1 V1 and M2 V2? Anyone? Please. Anyone, guys?
Doctor, is the initial concentration equivalent to final concentration?
Yes. Who's that? Govindraj?
Yes, doctor.
Yes, that is dilution, right? Thank you, Govindraj. Equal.
Welcome.
What Govindraj told us? Can you repeat it? The initial concentration.
Is equivalent to final concentration.
Okay. The initial concentration, right? Times the volume with the volume, right, is equal to the final concentration times the volume N1 V1 and M2 V2. For example, now I have, okay, this is your your activity right now. Okay, take out your pen and paper. All right. Let's say, okay, I have prepared 1000 ppm of the stock solution. All right, and then I need to prepare 100 ppm of zinc solution in, all right, in 100 milliliter volumetric flask, right? I want to prepare 100 ppm of zinc solution, all right, in 100 milliliter of volumetric flask from 1000 ppm of stock solution. So how much of this stock solution that I need to take to prepare the 100 ppm of the second solution, the right, that I need to prepare, all right? How much of the how much is the volume of 1000 ppm that I need to transfer into 100 ppm of volumetric flask? Okay, how much is it? What is the volume? 10 mil, right? Just calculate it. M1, V1, M2, V2. So what is my M1? My M1 is 1000 ppm, right? My initial concentration of the stock solution, right? Okay, 10 mil, right? So I have M1. M1 is my initial concentration, 1000 ppm. And what is V2? Sorry, M1. What is V1? So we don't know yet. That is the thing that this is the concentration. Sorry, the volume that we need to find. And we have already know what is our aims. We are going to prepare the 100 ppm of zinc stock solution, zinc solution in 100 mil, right? So after we calculate it, M1, V1, M2, V2, you don't know the amount of V1. So you need to take 10 mil. Thank you, Teh, Nadia, Azida, Aisha, and also Sue for calculating it, 10 mil. So I should take 10 mil from 1000 ppm, transfer it into the 100 mil of volumetric flask, right? So what I'm gonna do next? What I'm gonna do next? I have 10 mil of the 1000 ppm inside the 100 mil of the volumetric flask. Then what's next? We have shown you in the video previously. What I'm gonna do next? Someone
add
explain by
add distill water
yes.
until the calibration mark.
All right, Lim, thank you. So we fill it with the distilled water that Lim told us, right? Right. Then after this, I will explain to you why we use distilled water or any kind of a solution that we pretty sure that there is no metal inside it, right? Right. So in this case, Lim told us the distilled water. So we fill until the calibration mark, right? So that is when we reach the mark. So that is 100 mil. So we have now prepared, and after that we have to shake, of course, right, to make it what the keyword. What is the purpose we shake the volumetric flask? Yes, the keyword is homogeneous, right? Thank you to Lim, Al-Zahra, Aiman, Maisara, right? Aisha said mix thoroughly, yes. We have to mix it. We need to mix it to make sure it homogeneous, right? Like Shafiq said, like Azwan, like Lam Bun Hui said, like Chong Wan Ching said, right? We need to make sure it homogeneous. Sekata, right? Adun dengan sebati, macam buat kek kan. We need to make sure it homogeneous. If you make tea, right? You prepare a cup of tea, right? You put some sugar and then you just let the sugar be there at the bottom of the cup. Okay, I have put some sugar and you not stir it, right? What happens if you didn't? Okay, you do not stir your cup of tea with after you add some sugar. You cannot feel the sweet taste, right? Because the sugar is not homogeneously distribute inside your cup of tea, right? So this is the homogeneous term that we use in our daily life, right? But we didn't call it homogeneous. Mom, please prepare for me a cup of tea with homogeneous sugar inside it. Then your mom spill the tea, okay, on your head. All right. So that is homogeneous. We need to make sure it's evenly distributed, right, inside the solution. Right now, we have prepared a series. Oh, no, not yet. We have only prepared 100, right? And after that, okay, this is a question that we need to ask you. We have prepared 100 ppm from 1000 ppm, right? Can we prepare directly 1000 ppm of zinc solution directly? We do M1, V1, M2, V2 to prepare 0.1, 0.2, 0.34, and 0.5. Can we prepare it directly from 1000 ppm? It's quite a K-BAT question for you. Okay. Can we prepare directly from 1000 ppm to 0.1 ppm, 0.2 ppm? What happens if you calculate that? Okay, let me give you some figure, right? You need to prepare 0.1 ppm from 1000 ppm in 100 ml volumetric flask. Can you give me a figure of V1 that we need to take from the 1000 ppm of top solution? Please calculate. It's a similar calculation with the 100 ppm solution that you need to prepare previously. I have asked, okay? How much we need to take from 1000 ppm if you want to prepare 0.1 ppm of zinc in 100 ml of volumetric flask. So how much is the V1 that we need to take? 0.005 ml. I would like to ask you sincerely, have you watched the basic lab skill video that I have posted in the e-learning? That's a task for you. You need to complete to watch the video first before you can take the simulation result for experiment. Yes, we have watched, right? We are explaining to you in the video to use the pipette, right? With the palm that I use in the video. Palm and pipette. That is a very traditional one. But we need to teach you that. The basic thing in the analytical chemistry, right? After this, you will learn a lot of a modern apparatus. You have micro pipette. You only need to adjust the volume that you need, and then you just push the button, and then you can take the amount of solution that you need to take. That is a very common one we use in industries, in the modern labs. But we teach you a very conventional, traditional technique, right? You use it in biochemistry lab, of course, right? I use it. Right? Everyone in the the analytical chemistry in most of the lab. Okay, we use the micro pipette, right? The modern pipette where we can adjust. But we teach you, right, in the lab, the traditional one, right? If you watch the video, can we take 0.005 ml of the stock solution 1000 ppm to prepare the 0.1? Can we take it from using the pipette that we teach you in the video? Can we use it? The pipette that we teach you in the video, basic skill? Anyone? No, no, okay, cannot. Right, yeah, of course, no. Why? Why? Can you tell me why? Why? Yes. Okay, we have the idea. We cannot use that to prepare the 0.1 ppm concentration of zinc solution from 1000 ppm. We cannot take 0.005 mil using that pipette. But why? Because the volume of the pipette itself, right? Right? It is very, yes, Al-Zahra, thank you. It's very small amount and pipette is huge for it, right? How cool on earth you can take 0.005? I should give you some respect if you can do that, all right? Of course, the amount is too small. But if we have micro pipette, can we do it? We adjust the volume to 0.005 mil, right? And we take from the stock solution, all right? Okay, and then we put in the volumetric flask, and then we add some add the DC water or deionized DC water up to the mark so that we have the 0.1 ppm. Now you are proudly prepared 0.1 ppm zinc solution from 1000 ppm of stock solution. But guys, you should not do that. Yes, you can prepare it, but you should not do that. Why? This is also tricky for you, but I need to teach you. I need to tell you this thing. Why? And I would like to ask your idea first. Why you cannot prepare 0.1 ppm of zinc solution directly from 1000 ppm? Why? Anyone, please give me some idea so that I will know. You think about it first. Why? You should not. I didn't say that you cannot do that. You should not do that in this analytical chemistry. Yes, Yen K, but you text me privately, right? Easier to make mistake. That is the keyword that I want to hear from you. Thank you, Yen K. You make my day. Okay, all right. Because in analytical chemistry, right? In analytical, whatever analytical biochemistry and so on, in analysis, we are avoiding, right? We have tried our best. We will have to try our best. Remember to avoid the error, human error, systematic error, and all errors, right? Because it's easier for us to make a mistake there, right? And it will affect a lot in the concentration that we of the solution that we will prepare, right? You need to take 0.005. What happened is some of the solution when you put it in the volumetric flask didn't go directly to the volumetric flask, right? It will is stuck on the tips of the micropipette, and it will affect the concentration that you have prepared. It is not 0.1 ppm anymore. It's 0.8. It's not 0.1 ppm anymore. It's 0.08 ppm. You didn't get you will not get the good calibration curve because you have you make a mistake there, error, right? So to reduce the error, to avoid the error, we need to prepare, right? What we call that, from 1000 ppm to 100 ppm, and then from 100 to 10 ppm, from 10, right? And I think from 10 is enough for us to do up to 0.1, 0.2, 0.3, 0.4, 0.5. Okay, calculate. Okay, from 10 ppm, right, of top solution, how much you need to take to prepare 0.1 ppm in 100 ml volumetric flask. Okay, and give me a figure for that. From 10 ppm, how much we need to take to prepare 0.1 ppm of zinc solution in 100 ml volumetric flask. right? You have tell us the answer, right? How much? 10 mil. Okay, so is it possible to take 10 mil and by using the by using the pipette and transfer into the 100 mil volumetric flask to prepare 0.1 ppm? Is it possible? Yes, of course. Okay, it's possible, right? We can use our pipette in the lab to prepare it, and we have avoid errors in doing that, right? In preparing the calibration solution. Why we need to avoid all these errors? Okay. After this, I will tell you. I will tell you after this. All right. Okay. Now let us resume the video. Right, guys. After I play and tell me, you can hear the sound of the video or not?
I'm going to make up the concentration to X plus 1 ppm, X plus 0.75 ppm, X plus 0.5 ppm,
Right,
X plus 0.25 ppm, and X plus 0.0 ppm by adding certain amounts of volume from the working standards that I prepared earlier. The volume will be made up to the mark using distilled water, and you have to be very careful when you are doing that to make sure that you get the meniscus right on the dot. Now, I think we are ready to perform our AAS analysis. Come, let's go. We go to the AAS machine and do the analysis. Come, follow me.
Assalamualaikum dan salam sejahtera. Nama saya.
All right. Sorry, I need to stop again. Okay. And in the video that we have watched, sorry. So it's happened again. Guys, can you hear me? Can you hear me now? Yes, okay, good. But I don't know what happened to my screen view. But it's okay. Okay, we search for the standard addition method in AAS. I search for image, right? I would like to show you the graph. Okay. Okay, let us watch the video, I think.
If you manage a team, you should be.
That is an ad.
In this video on the standard addition method, you should be able to compare and contrast the utility of using a calibration curve method, the concentration, and also design. Standard addition is another method that's related, but it's a really
not so good video, I think. Okay. My computer is good right now. Sorry. Wait for a while. Okay, now it's okay for me. All right, guys. Just now we have forgot about the standard edition, right? Just now we have prepared this, a series of a calibration plot, the normal calibration what? 0.1 to 0.5, let's say, right? Okay. Now, just ignore about the amount of the, concentration, okay? Let's say we have prepared 1, 2, 3, 4, 5, 6, 5, all right? And to prepare the zero concentration, all right, we use the blank, all right? Remember in the procedure, okay, you read the procedure, you have to prepare blank, right? Okay, so what is blank? Okay, remember when you prepare the calibration solution, for example, the normal calibration solution, not the standard edition, right? You prepare 0.1 to 0.5. After you put the certain amount, after you calculate M1, V1, M2, V2, you put what solution up to the mark? What kind of solution you put up to the calibration mark? Anyone? Okay. What solution did you put into the volumetric flask up to the mark to prepare the calibration solution? Yes, distilled water, right? Or deionized water, ultra pure water, meaning that water, only water, right? A pure water, right? We are analyzing metal. We don't need any metals inside the distilled water, right? Because it will disturb the concentration of the metals inside the calibration solution. All right, that distilled water we consider as a solution without any analyte inside it. For example, today we are analyzing the zinc, right? So we need to use the distilled water that we assume that there is no zinc inside it, right? Okay, so this solution is considered as a blank. Okay, so we use it only this solution to run with the AAS instrument, so that the AAS we read this is a blank, right? This is a solution without any zinc inside it. Okay, now we're analyzing zinc, right? We put the hollow cathode lamp to with the zinc energy source, right? The wavelength is zinc with the zinc energy, right? And we run the blank from the distilled water, you said here, right? And then we told the instrument. Remember, the instrument is not clever, right? The term that I use to teach all my students. We need to teach them how to detect the concentration. They only can tell us the absorbance, but we need to teach them the concentration. So how we need to teach them the concentration? First, we put a blank, right, which now the distilled water for the normal calibration, right? We put the distilled water, right, and then we tell the instrument that is 0 ppm of zinc, right? So it is 0 here. We will detect 0. After that, we put, let's say here is 0.1. Okay, 0.2, 0.3, okay, 0.4 and 0.5. Sorry. Okay. So the first solution that we run for the AS to read the concentration is 0.1 ppm. And let's say the AS read the absorbance, right? And it's a plot here. Okay. After that, 0.2 is here, right? 0.3 here, 4 and 5, right? So we get the R square of the linear curve, okay? 0.9983, right? This is the equation, right? What is the R square? What is the R square value for linear curve, okay? For linear graph, okay? What is R square? For linear equation, what is R square? Anyone? Correlation coefficient, right? Okay, let's say when I plot, it is our calibration solution that we have prepared is with an increasing concentration, right? With a constant increasing concentration, right? 0.1, 0.2, right? 0.3, 0.4, 0.5. What happens if the plot is not so linear, right? Some of the point is not in the straight line. Example, this one is not here. This one is not here. Okay. It is outside of the straight line, right? This one is good, right? Almost all in the straight line. So what happened to the R square value? Decrease, right? Not more 0.9983. This is so good. Maybe it become 0.8. All right. 7, let's say, for example, this is only for example, right? Right? Maybe 0.91, right? Okay. It will affect the value of R square when the points are outside of the straight line. Okay. And then what happened? Okay. If all the point is perfectly on the straight line, what is the R square value? It's perfect on the straight line perfectly. The value is 1, right? But it is almost impossible for human. We have error in doing this, right? So the perfect one, if we got the R square value, right? 0.9999 and 9 more, right? But okay, for the analytical science, right? It is acceptable, okay, for us. Okay, this is acceptable value with the less error in preparing. Remember, if you prepare the calibration solution wrong, a lot of error, right? You dilute directly from 1000 to 0.1, for example, you will not get the good R square value. A lot of error will occur during preparing the calibration solution. Then you will not get the good R square value. Okay, but it is acceptable in the analytical world. You must get 0.99. How many? 5. Okay, good from Lim. Okay, 0.995. This is the sorry, how to annotate this? Okay, this is the minimum one. You should get this right in the analytical science, right? If you want to discuss any results, this is acceptable one. If you get the value of R square 0.91, okay, you forgot about presenting your data to the analytical work. I mean, in scientific work. For example, in your journal, you want to write a journal, right? A science journal. Don't forget about it because you get the R-square value is 0.1. But there is some exclusion. For example, in the biological experiment and so on, they have any other value acceptable for that, right? But the most common one is 0.995, right? The perfect one is 0.9999. Okay. Yes, someone got this value of R squared in preparing the calibration solution, right? If you also I think if you regularly do this calibration solution, right? You know where is the mistakes that you need to avoid. You can have this. Okay. Okay. And then what is the difference of normal calibration solution and the standard addition solution, right? If you read the from the manual, right? Determination of zinc using the standard addition method, right? Where is the difference is? Okay, let me show you. Okay, wait for a while. Okay, wait. All right. Now, for C, okay, in the lab manual, in part C, procedure C, is determination of zinc using the standard addition method. Right? Instead of preparing the series of calibration solution with the increasing concentration using the distilled water or ultra pure water or deionized water as the blank, right? To fill or to prepare the calibration solution. Right now, we have to add some concentration of our sample. Right? Remember? Okay, sorry, I need to tell you again. Sorry for a while. Right, can you see the photo again of the linear calibration? Okay, so what can we do with this calibration plot? Right, after the instrument detect the the absorbance, and we tell the instrument, okay, this is 0 ppm, and we have we analyze 0.1, and we tell the instrument, okay, we set in the instrument this is 0.1 ppm, 0.2. Remember, the instrument don't know the concentration. The instrument only detect this one is what? the response, right? Which is for AS, it is the absorbance, right? So with this increasing absorbance, we tell the instrument this is 0.1, 0.2, 0.3, 0.4, and 0.5. Okay. Okay, now the instrument, okay, this is the concentration. If this absorbance, the instrument know, oh, this is 0.1. If this the absorbance amount, oh, this is 0.2. The concentration is 0.2. Now the instrument also learn this is 0.3. This is 0.4. This is 0.5. After that, okay, we detect the unknown instrument, the X, right? Sorry, the unknown sample, the X, right? And we don't know the X concentration, but we know that it is within this within 0 to 0.5 ppm. Okay, that's why we prepare the calibration solution series 0 to 0.5, 0.1 up to 0.5. It will rely between this, okay, concentration. Let's say it is the concentration is actually 0.35 ppm. So when the instrument detect from sample X, right? Sample X, the solution is sample X. When the absorbance is around here, sorry, so the instrument detect from the experience that we teach the instrument, this is the concentrate, this is the absorbance, and this is the concentration. Now the instrument know if this is the absorbance, so referring to the calibration plot, okay, so this is the concentration. Okay, so the instrument know this is 0.35, sorry, ppm. Okay, this is the use of calibration solution. We teach the instrument on how to know the concentration based on the response. In this case, AAS, the response is absorbance. Right. So what happened with the standard addition? Right. So for standard addition, okay, what is the difference? If you can read the procedure C, the difference is we put some exact amount of sample, right? For example, X plus 0, okay? All right. Okay, calculate the volume of zinc stock solution needed to prepare a series of 500 ml standard with concentration of X plus 0 0.00, 0 0.25, 0 0.575, and 1 ppm. Okay, what is X? Right? We add a exact amount. Remember in the video, I have shown you, right? Before I walk to the AAS instrument room, okay? How much of sample that I put inside the volumetric flask for all the volumetric flask for series of calibration solution. How much? In the video. Or you need to watch again. Right, sorry, I need to share this.
Volume from the working standards that I prepared earlier. The volume will be made up to the mark using distilled water, and you have to be very careful working standards that I prepared earlier. The volume will be made up to the mark using distilled water, and you have to be very careful when you are doing that to make sure that you get the meniscus right on the dot. Now, I think we are ready to perform our AAS analysis. Come, let's go. We go to the AAS.
Right. So the exact amount of sample that I put all in all the calibration solution series for the standard edition X, right? In the procedure is 20 mil. Am I correct? You can read in procedure C, right? Pipette 20 mil of the water sample to each flask and finally add the ionized water, right? We put a similar volume in every volumetric flask, okay, with different concentration of with different volume of the stock solution, so that we prepare X plus 0, meaning that blank, right? We didn't put any of the standard solution from stock solution, right? And then we prepare 0.25 ppm with added with X, right? What is X? 20 mil of water sample that we don't know what is the concentration. All right, why we use this standard addition method instead of using only a normal calibration technique? This is a linear calibration, preparing a series of concentration, right? You need to find out why, okay? So that you can discuss in your lab report. You need to find out why we use this standard addition method, right? Okay, someone have answered. Okay, to decrease matrix interference. Okay, what is matrix? Our sample, right, is from a various type of we have a various type of matrix. What is matrix? For example, we have a river water sample. So our analyte is zinc, but the matrix, the other substance, the other compounds inside the sample maybe can interfere, right? Can disturb in our yes, anything but analyte. It can disturb our reading process, our analytical process to detect the analyte. So that to avoid that interfering in our analytical process, so we should do this standard addition method. We add exact similar amount of similar volume of sample inside all the calibration solution, right? So that it's no longer yes, we prepare just like 0.25 ppm, right? We take the certain amount M1 V1 from M1 V1 M2 V2 equation from stock solution to prepare 0.25, 0.5, 75 and 1 ppm. But instead of using all the distilled water, right, or deionized water to fill up the volumetric flask up to the mark, we put another X amount. For example, this 20 mil in every flask, and then we top up with the deionized or distilled water up to the mark. So that in the series of calibration solution, the concentration that we'll detect by AAS instrument is not purely 0.25 ppm, but there is also added amount of concentration for zinc from the sample X, right? X amount. In this case, from 20 mil of the sample, it will give some extra in the concentration read by the extra value of the concentration read by the AAS, right? So that the graph will be no longer a calibration plot that like previous one. It will be like this, okay? Okay. It will be like this, okay? If a normal plot, we don't have this one, extrapolate, okay? For example, we have prepared, you will not get this extrapolate automatically, okay? You have the normal calibration plot, but it is, sorry, need to remove the annotate, okay? But it is not from, it's not from 0, like the normal calibration plot, okay? Why previously we get 0? Because in our DC water or deionized water, there is no analyte. But now we have some analyte that gives some absorbance for the AAS from the X amount. For example, in the blank, right? X plus 0.00, we don't put any of the standard solution for zinc inside it. We just prepare X, right? 20 ml of sample and just mark up with the deionized water or distilled water, and it will detect some amount of absorbance, right? That is from the 20 ml of the sample. It's not here, no longer here, because previously we only use the distilled water or deionized water, which is zero analyte. So now we have some absorbance, right? And then we have increasing concentration, of course, because we increase the standard solution amount in every flask, in the every volumetric flask, so that we have increasing concentration or increasing absorbance read by the instrument. And then, okay, we have to extrapolate the graph. Okay, after we get after we plot the graph, okay, with the when the graph started with some absorbance here, okay, which is no longer from zero with some absorbance here. Okay, we need to extrapolate, okay, the graph, okay, and then what is the concentration of zinc inside the unknown x from x is here. Okay, of course not negative value. Okay, from the extrapolate in the negative side. Okay, you need to you know what, take the positive amount lah. Okay, take only the amount. Okay, for example, it is 3. Okay, negative 3, meaning that in x, okay, amount of sample, for example, 20 ml of sample, it is 0.3 ppm. Okay, so this is how the standard addition method used. Okay, now we watch the remaining part of the video. I hope you can understand that. Now we watch the remaining part. Remaining part of the video.
AAS machine and do the analysis. Come, follow me.
Assalamualaikum dan salam sejahtera. Nama saya Azaini bin Ishak, telah bekerja di PM ini selama 30 lebih tahun. Dan apa yang saya nak katakan di sini, sebelum anda prepare bahan-bahan anda perlulah menjaga SOP preparation, safe procedure, di mana kamu kena guna PPE, kena guna goggles, mask dan glove, ya. Dan apabila datang ke sini, ada SOP penggunaan alat supaya untuk menjaga jangka hayat alat ini, ya. Dan alat ini namanya Pekin Hammer model AAS 400. Daripada Pekin Hammer Analysis 400. Okay. Dan sebelum anda onkan semua, anda kena jaga SOP alat ini, di mana bukakan gas C2H2, di mana acetylene digunakan, gas acetylene, dan onkan device instrumen ini, dan PC onkan sini. Onkan alat ini dan PC, dan selepas itu kita onkan kompresor di luar, iaitu oksigen yang akan membantu pembakaran. Dan sebaliknya, bila nak tutup, kita offkan sana kompresor, device dan PC, dan barulah device dan gas. Dan sebelum untuk menganalisis, kita gunakan fume hood ni, sebab kita berada di dalam keadaan yang boleh kata bahaya, di mana kita menggunakan logam-logam berat. Dan di sini saya terangkan bagaimana fungsi alat ini. Alat ini berfungsi untuk menentukan sesuatu kepekatan logam yang kita tidak tahu, tapi kita tahu logam sebenar. Katakan kita nak cari zinc, kita dah tahu zinc dan tapi kita tak tahu kepekatan dia sebenar. Ya, dalam di sini menggunakan unit ppm. Dan di sini saya terangkan perkakasan alat-alat ni. Ni dipanggil nozzle. Dan keseluruhan ni dipanggil chamber. Depan nozzle ini ada satu berbola bit. Dan depan berbola bit ada spoiler. Di mana bila dia menyedot, dia akan mengatomize seperti kamu gunakan perfume atau paints atau spray cell top. Bentuk dia begitu. Dia akan mengeluarkan satu percikan yang sangat halus dan smooth. Dan apabila dia sedut di dalam chamber ini, dan atom-atom tadi akan teruja, dia akan chopping daripada dalamnya. Dia akan teruja atau atom terhasil dan terbebas di atas ini. Dia akan putuskan rantaian atom dan atom-atom tadi akan terhasil di atas. Dan kita gunakan source. Kita nak cari zinc, kita gunakan lamp zinc. Sebaliknya, kalau kita nak gunakan, kita nak cari cadmium, kita gunakan lamp cadmium. Ini dipanggil hollow cathode lamp, di mana dalam dia ada anode dan cathode cadmium lah. Kalau kita guna zinc, zinc lah. Hollow cathode lamp. Di dalam ini ada 4 housing, tapi kita boleh gunakan satu dalam satu masa. Dia tidak seperti IC PMS, dia boleh gunakan satu saja. Okay. Dan bila atom-atom tadi telah teruja di atas benda ni, dia panggil gas benda. Di mana kita gunakan lamp cadmium. Cadmium tadi akan menyerap cadmium saja. Kalau yang terbebas itu cadmium, plumbum atau sebagainya, dia sebab kita nak cari zinc, dia akan serap zinc saja. Bila dia nak absorb, dia akan hantar ke detector di sini dan terus dia hantar menjadi spektrum. Dan data-data ini akan anda olah balik menjadi membuat laporan dengan kepekatan yang sebenar, di mana anda akan mencari YNX campur C, kecerunan yang sebenar yang akan anda laporkan. Buat laporan Dan rasanya tak jaga ni. Dan sekarang kita gunakan teknik flame, di mana dia menggunakan api. Ini dipanggil teknik flame. Kita ada 3 teknik, hydrat dan juga graphite. Di mana jika anda tidak mendapat hasilnya dalam kepekatan ppm, anda boleh cari, bukan bermakna anda tidak dapat, tapi anda boleh cari dalam kepekatan yang lebih rendah, ppb yang menggunakan hydrat dan graphite. So, di sinilah dia akan menyedot. Semua sampel-sampel anda ataupun standard semuanya dalam bentuk larutan, bukan pepejal. Dia akan menyedot seperti mana yang saya terangkan tadi. Dia akan mengatomize dan atom-atom tadi terhasil dan terbebas teruja di atas akan diserap oleh lamp zinc. So, dia akan hantar ke sini sebagai spektrum dan data-data anda akan olahkan semula di dalam Excel, baru dapat kepekatan dia yang sebenar. Sekian, terima kasih. Okey, ini adalah seperti mana setiap Pengoperasi alat ini akan membuat satu kalibrasi yang sebenar. Kepekatan 0.3 ppm akan mengeluarkan bacaan setidak-tidaknya 0.18, sebenarnya 0.2. 18 dah memadai. So
video tu dia cepatkan dia bunyi macam tu sikit. Right, if you can see there, that is the absorbance, alright, detect, okay. As I told you, the instrument know only the absorbance. We have to teach the instrument, okay. Belakang tu, okay, you can see the concentration that we set. Dapat on the screen behind of continuous graphic tu, you can see replicate data blank, okay. Then you can see standard concentration 0, we set 0, okay, and the signal is there, okay, we set to 0, okay. See the atomizer there, okay. There, the graph of the absorbance, right, versus the concentration. Okay, that is the end of the video. Okay. Now, okay, we have reached to the end of the virtual lab session. Okay. Now, I'd like to hear from you guys if you have some question to ask. Anyone? You have question, guys? You can open your mic or you can type in the chat room. Okay, this is privately asked to my chat. Okay, doctor, the data for absorbance will be given. Okay, of course, for this virtual lab session, okay, the simulation result or just use the previous analysis result. Okay, I will scan the raw data from the AAS, okay, and give it to you, okay, for the for B part, okay, for procedure B, determination of zinc using linear calibration method, okay, I will give you together with the part C, okay, using standard addition method. Then you need to discuss about the you need to plot the graph as well, okay. For part B, you need to do linear calibration plot, okay, from 0 to what is the amount, 5 calibration concentration, okay, and then you need to do C, okay, with the extrapolate, okay, graph is extrapolate, and then you need to get the R-square value, of course, from the result itself, okay, the R-square value will be given there on the AAS result sheet, okay, and then you need to discuss, okay, of course you didn't do that, okay, this is simulation result, but if the R-square is not in a good value, is lower than 0.995, you need to discuss what happened, okay, due to some errors in preparing the calibration solution. All right, you need to discuss, okay, even though it is a simulation result, okay, if the result of the R square is good, okay, you also need to discuss why, because the calibration solution have been prepared, okay, carefully without reducing all the possible errors, okay, and that's why you get the good R square value, okay. Need to discuss, okay. Even though this is a simulation result, we can use Excel. Yes, of course, you can use Excel and calculator to get the equation. Of course, you need to use calculator. Okay, you cannot calculate it, or if you good enough, you can calculate it without a calculator, right? For the R square value. Of course, we can use the Excel. Okay, because I've told you. Okay, if you are here in experiment 1 session, we have this site that you can use handwritten and typed version of lab report, but you need to be sincere that you did not copy paste directly from any sources, because I will check for Turnitin after this, right? If you get caught for the plagiarism, okay, it is bad for you lah, because your mark will be deducted, all right? And then it is, rugi lah, for lab session, you get a low mark for this, okay? You have put some efforts to orang lain sedang cuti, okay, other students now on leave on the for the semester break, but you need to pay attention for this course, for this special semester to finish it, but you need to do in a good way, right? So we can get the equation R square with the statistic part in the calculator. I was asking about it. Well, what you R square with the statistic part in the calculator? Yes, of course. Okay, if you know how to use the scientific calculator to get the R square value, I think there's some method for that, but it's easier to use the Excel. Okay, for submission, one group, one submission, or everyone submitted. Okay, of course, for lab report submission, only the representative of the group, not all of you submit the lab report. Okay, pening lah saya nanti kan, tengok setiap orang hantar. Saya pula kena check kan, which group is this person from. Okay, remember and tell all your friends that only representative from one group, okay, submit the lab report, not all of you. Okay, of course in the submission, you kalau wakil your friend submit it, okay, then it appear to me that you didn't submit. Of course I know that, but this is just a platform for you to submit. Okay, we the one who will mark your lab report and decide on marks. Okay, so this is the platform you to submit it in the e-learning. All right, Kamil Raj. Okay, welcome. Any question? Other questions? Right. Any other question? Can you understand, guys, what we are doing today? Analyzing or the determination of zinc by using linear calibration and also standard addition methods using AAS. Okay, can you understand what is linear calibration, what is standard addition? You can differentiate that, right? Give me thumbs up. Okay, all right, good. Okay, then you are ready to prepare the lab report for experiment 3, right? Guys, we have reached the experiment 3. Tomorrow is the last one, experiment 4. Okay, and stay tuned for those who haven't finished experiment 4 yet, but all of you are invited for the lab session, for virtual lab session. Okay, about the negative X, should we directly convert it to positive? Yes, of course, that is the method. That's directly convert it. We just need the value. Okay, the value will represent what is the concentration inside the X. Okay, it's 20 mil of the sample. Okay, remember the concentration is not directly. If you get X is 3 ppm from the calibration plot, does it mean in the sample you have 3 ppm? No, it is in 20 mil of the sample. Okay, so what is in all sample? Okay, yes, Al-Zahra. So -3 is 3 ppm. But is it 3 ppm in the whole sample? You need to convert it, think it. Okay, you need to think it how to calculate. Okay, for the concentration of the sample, it is only in 20 mil, right? Not in whole solution that we prepare. Okay, so how much you need? How you need to calculate this? You should think about it. Okay, I should not tell everything to you. You need to think by yourself. Okay, you need to discover, to search how to calculate the solution, the concentration of the solution using the standard deviation method. Refer to any journal. Okay, of course, guys. If you refer to the lab manual, okay, you are also given the, the rubrics, all right, on how to prepare the lab report, right? I should remind you again. There's some marks there on everything that you need to prepare. Okay. Logbook. I already told you for this virtual lab session, the logbook is represented by your attendance mark. Okay. And then participation and practice. Okay, we will do that for you. The marks. Okay, we know how to do it. Okay. Abstract, introduction, material. Okay. Remember in the reference. Okay. Remember you should have at least 5 reference from the journal or books or other sources. All right. So if you get the information from any sources, just put the citation and put it in reference. The minimum is 5. Okay. So that you can get how many marks? Sorry, minimum is 4. Okay. The minimum is 4 reference, and then you can get 5 marks for that. If you put only 2 reference, so you cannot get 5 marks for that. Okay. It is easy, all right, for us to mark. Okay. Okay, if you don't have any question, shall we start now for this experiment 3? Okay, we have other lecturer now. Mr. Daniel, do you want to add something? Mr. Daniel, you want to add something before we end the session? Thank you to Mr. Lukman who prepared the video, right, for the whole virtual lab session. Such a good video. Okay. If you don't have other question, okay, and have you all filled the attendance? Okay, I should give the attendance link one more time for experiment 3. Okay, this is the attendance. Please fill it. Okay. All right. If you don't have any more questions, all right, I'd like to thank all of you to stay tuned until the end. All right. And good luck in preparing your lab report. I will, for sure, I will try my best to upload the simulation result of the AAS by today, by hook or by crook. Okay. Or I think by today I can upload it, but you need to, yes, after before submission, of course, you need to download the simulation result for the AAS first. Okay. And you prepare the lab report based on that. Okay, if you don't have any question, I think that's all for today for experiment 3. Thank you so much. And see you again tomorrow. I will not be the host for tomorrow because I will get my second jab tomorrow. My second dose of vaccination. Okay, AstraZeneca tomorrow. So, okay. Oh, Aisha, laugh, laughing, Aisha. Okay. I'm afraid of that tomorrow. Okay, so maybe Dr. Afiq or Mr. Daniel will be the host for tomorrow. And then, so we have only 4 experiments, right? We finish by tomorrow, and then that is the time for you to prepare that report. Thank you so much, guys. Okay, and assalamualaikum and bye-bye.
Thank you, Doctor.
Yes, most welcome. Yes, welcome.
Thank you, Doctor.
Okay, welcome.